What happens when a helicopter tail rotor fails? Watch this video. Hello, welcome to the channel. I hope you're all well. So, very quick video here. What happens to a helicopter when the tail rotor, the anti-torque system, fails? So, when the helicopter is in full operation, you've got a main rotor, the rotor that sits on the top of the helicopter, that spins. Now, some helicopters, most helicopters spin counterclockwise. There are some that spin clockwise. So whichever direction that the main rotor is turning, the fuselage will naturally want to turn in the opposite direction. That's why you need something on the tail section of the helicopter fuselage so that it can turn the nose of the helicopter in a particular direction to counteract the natural tendency of the fuselage to want to turn in the opposite direction of the main rotor. So that's what we call a torque effect, and then there's an anti-torque effect, the tail rotor control system. Now there's a tail rotor system. It could be a tail rotor, it could be a fenestron, it could be a Rotor system. But essentially, they're all doing exactly the same thing. So when this fails, let's just say there's a linkage problem, or the blades fall off, or there's some kind of impact, some kind of mechanical issue here that stops this working, then what's going to happen? When the helicopter is in a hover, then there's going to be no anti-torque system to counteract that fuselage turning right. So the only way to stop that fuselage turning right or left, depending on which way the fuselage turns. So if you've got a counterclockwise rotating main rotor, then the fuselage is going to want to turn right. If you've got a clockwise rotor, then it's going to want to turn left. So let's just say for the most part, we're talking a right turn. So if the nose wants to go right, then you're going to put a left pedal to push the nose of the helicopter straight on. But if you've lost the effectiveness of that tail rotor, then all of a sudden that nose is just going to spin increasingly right until you lose total control of the helicopter. So the only way to stop that is to what we call chop the throttles or just turn off the engines. And you do that by just turning off the throttles really quickly, going to manual override. That decreases the power to the main rotor, and that gets rid of that torque effect. So all of a sudden then you'll stop that right turn, or certainly reduce it at a rate where you can just land the helicopter. Now, of course, what's happening at the same time is once you've chopped the throttles, there's no power to the main rotor to overcome the drag of the blades. So the helicopter will settle. You're going to lose height. So you've got to be able to manage that so you can nettle it down to the ground. Okay, so let's just say you're at takeoff or a high height, let's say 150 feet, 200 feet, something like that. Now, dependent on the helicopter type and the model, of course, it will determine at what stage you might be able to recover this. And this is what we call within the height velocity diagram of the helicopter, in terms of this is like a big danger area. So some helicopters have takeoff profiles that try and minimize the time within this height velocity diagram as well. But let's just say you're climbing out a couple of hundred feet and you have a tail rotor section. So you're still at 0 speed, airspeed flight. You're just taking off. Then all of a sudden you're going to have to chop the throttles again and dive down and then try and get onto the ground as well, because you're going to lose that directional control. If you've got enough height thereafter to be able to nose forward and try and get airspeed, you're going to try and get as much airspeed as possible. Once you've achieved forward airspeed, let's say beyond 50 knots, some case it could be 60, 70 knots, whatever it is, then the tail rotor is less effective anyway, because you've got airflow over the fuselage. You've, let's say, got horizontal stabilizers. You've got a vertical fin on the tail section that give it the helicopter directional stability. So that's what you're trying to aim to achieve, in that you get forward flight, so you get directional stability from the airflow flowing over the fuselage. But if you're so close to the ground, or you're at a height where you can't get airspeed, then you're going to have to enter auto rotation, lower the lever, chop those throttles, so you're descending, and then you're hoping you get enough cushion and enough power in the collective alone just to cushion the landing as well. Now, once you're in forward flight, as I say, 50 knots, 60 knots, 70 knots and above, then you're going to be relatively stable because the tail rotor system is largely ineffective at speed. You're only using it for balance, aerodynamic balance, and aerodynamic efficiency rather than maintaining directional control, because the airflow over the fuselage itself, and as I say, with horizontal stabilizers or vertical fins, will keep the aircraft stable in terms of directionally stable, in terms of not pitching up and down, and not having any kind of lateral movements as well. So it's crucial that at slow speed flight that the tail rotor section is working correctly. At higher speed flight, it's largely ineffective. But it's in those scenarios when you're in hover or when you're relatively close to the ground or you're on a takeoff, that's when it's most crucial for tail rotor control failures or tail rotor failures in general. Hope you found that useful. If you like what I do here, just keep on watching the videos and I'll catch you again. Bye now.